All right, the next thing I want to do is to work on what I'm going to call matrix algebra. I'm blending sections 2.2 and 2.3. So we're going to use a little bit from each section here. And by matrix algebra, what I mean is I want to start to manipulate matrices themselves. I'm not going to think of working with a matrix and doing row reductions. I want to actually simplify or actually do algebra with matrices. So for example, let's say A is the matrix 1, 2, 3, 4. B is the matrix 5, 1, negative 1, 0. And then what I want to do is I want to solve for X. And you can call X, if you like, a generic matrix A, B, C, D. We don't really need to do that, but solve for X. I just want to emphasize that it's a 2 by 2 matrix. So I want to solve for X in the equation 2A plus 4X equals 3B. So what I want to do is I want to solve for X, figure out what is the matrix X that's going to satisfy this equation. And this is really no different than solving an algebra equation like you would in high school, grade school, kindergarten, whatever it is. Obviously, it's not kindergarten, same joke as yesterday. So you have 2A plus 4X equals 3B. We're going to solve for X, so we're going to get everything else that's not an X on one side, and we're going to subtract 2A from both sides. Okay, so we can subtract 2A from both sides, and then X, if we want to get it by itself, I'm going to multiply everything by 1/4. Let me just add one extra step here. I think this is obvious, but I just want to make sure that everything is good here. So what I'm going to do is when I say divide both sides by 4, I need to be a little bit careful. I'm going to multiply both sides by 1/4. I'm allowed to multiply both sides of any matrix equation by any non-zero constant. 1/4 is certainly non-zero. And then we can use the associativity of scalar multiplication, and the 1/4 times 4 we can group together. That's times X. And then we'll use the distributive property of the right side for the right side of the equation. So this will be 1/4 times 3B minus 1/4 times 2A. And then again, you can use the associative property of scalar multiplication. And you end up with X being equal to 3/4 B minus 2/4 A. And so it turns out that X is going to be whatever that matrix is. So this will be 3/4 times matrix 5, 1, negative 1, 0, minus 1/2 of 1, 2, 3, 4. So fractions ahead, but no big deal. This is going to be 15/4, 3/4, negative 3/4, 0, minus the matrix 1/2, 1, 3/2, 2. So altogether, this is going to be, let's see, 1/2 is 2/4, so that'll be 13/4. 3/4 minus 1 will be negative 1/4. Negative 3/4 minus 3/2. 3/2 is 6/4, so that'll be negative 9/4, and 0 minus 2. Okay, so it turns out that that's going to be the matrix X that will satisfy that equation. So this is the kind of thing that I mean for matrix algebra. All right. One other idea just to talk about in matrix algebra, and I want to think about, so I want to go back and think about a just regular algebra question. Let's say I want to solve 5x plus 7 equals 4. So let's say I want to solve the equation for X. This is just now a regular old algebra question. How would we do that? Well, if 5x plus 7 is 4, that means that 5x must be negative 3. So we could subtract 7 from both sides. And then we're going to divide both sides by 5. We have to be really careful here because there's no such thing as dividing by a matrix. The way I want to think about this is that I'm going to multiply both sides, by the multiplicative inverse of 5. I'm multiplying both sides by 1/5. And when we do that, the x will be by itself, and we end up with -3/5. Okay? Multiplying by a multiplicative inverse is the operation that will translate to matrices. So let's say I want to solve ax plus b equals c, where a, b, c, and x are 2 by 2 matrices. How could we do that? When does this have a solution? Maybe there's infinitely many solutions. Maybe A is the 0 matrix, in which case we just have to check whether or not B and C are equal. And if they're equal, there's infinitely many matrices X that'll satisfy this. If they're not equal, there's no solution. So we need to figure out, is there 0 solutions, 1 solution, infinitely many? To do that, I actually have to give you values for A, B, C, and X. Which I'm not going to do here in general yet, but I just want to talk about the process. How could we solve for capital X? And it's going to be exactly what we did up here, exactly the same. We're going to subtract this matrix B from both sides. So AX is going to be equal to C minus B. And then how do we get rid of the A? Well, we need to multiply both sides by the multiplicative inverse of A. So this is going to be A inverse times C minus B. And so A inverse times A times X. Again, once we get used to the associativity properties here, I can just start to take some liberties and do all these steps at once. But I can use the associative property and a little iPad magic to move the parentheses around. So I could put the parentheses around the first 2 matrices, in which case this is going to be just X. This is the identity times X, which is just X. So this tells us that the matrix X is going to be A inverse times C minus B, and all seems fine. The only thing that we have to check is that this really only works if A inverse exists. So if A inverse exists, then everything is fine. And you get a unique solution. X is whatever this matrix product is, whatever this term is. If A inverse does not exist, then there's not a unique solution. And if A inverse doesn't exist, we would have to actually have values of A, B, and C to determine whether we have 0 solutions, infinitely many solutions, and so on. Okay, so that's the idea. Now, what I want to do is I want to actually redo a problem or do something that's kind of old news. I want to solve the system. And I want to solve the system that's going to be 4x plus 3y equals 10. Let me make sure I can do this right. 3x plus 2y. I just want to make sure I don't screw up the algebra here. Is 15. Okay, so what I want to do is I want to solve this system. And let me actually use, I'm sorry to go back, let me actually use, instead of x and y, let me use x1 and x2. This doesn't really mean anything differently, it's just going to be a little bit easier to write it this way. So again, I just want to double check that I'm doing this right. Sorry. So what I want to do, I'm making this up on the spot, sorry. So I want to solve 4x1 plus 3x2 is 10. 3x1 plus 2x2 is 7. Okay. Now, the way I want to do this is I want to do this using matrix algebra. And so even though it doesn't look like this right away, you can write this as a matrix equation. So if I were to take, so notice that I could write this as the matrix 4, 3, 3, 2 times the variables x1, x2 equals 10, 7. So if we were to multiply these two matrices on the left, we'd end up with 4x1 plus 3x2, and we want that to be 10. And then likewise, 3x1 plus 2x2, we want that to be 7. So it turns out you actually can write it like this. And so I can actually write it as ax equals b, where A is the coefficient matrix. It's the matrix 4, 3, 3, 2. X is our variable matrix, so it's got components x1 and x2. And B is our constant matrix, which has terms 10 and 7. And so AX equals B, we could solve this. So notice that AX equals B is going to have a solution. X is A inverse B. Let me again, just because this is new, let me hammer home how that works. If we were to multiply both sides by A inverse, what happens on the left? Well, the A inverse times A will cancel and give us the identity. And so this leads us to X being A inverse times B. And what this tells us is actually something that's very important and very crucial, and we'll use this over and over and over and over during the semester. This tells us that if A has an inverse, in other words, if the determinant of A is non-zero, then AX equals B has a unique solution. I know it's a unique solution because I have an explicit form of the solution written. X has to be equal to A inverse times B, whatever that works out to be. In order to figure out what that turns out to be, we have to find A inverse, and then we'll compute that matrix product. So this again is a very important fact that we're going to use over and over. And again, the unreasonable usefulness of determinants is going to be present all semester. So if the determinant's non-zero, then AX equals B has a unique solution, and that solution is X is A inverse times B. So let's go ahead and do this. What I want to do then is we need to find A inverse. And there's a few different ways to do it. So we need to find A inverse where A was our matrix 4, 3, 3, 2. There's a few different ways to do it. The first way that we could do it is just by taking our matrix A, augmenting it with the identity, and then trying to get the identity on the left, and then whatever matrix we end up with on the right is our inverse. So that's what I'll do here. And there's a few different ways that we can get the identity on the left. So we want to start by getting a 1 in the top left. There's a few ways that you can do that. You can, if you're not one for creativity, and if you don't care about fractions, you can just divide both sides by 4, and then you'll have 1, 3/4, 1/4, 0 as your first row. If you want to be a little bit more creative, and there's lots of different ways to get to the right answer, one other way you could do it is to replace row 1 with row 1 minus row 2. So notice that they differ by 1, so you can use that to your advantage and say that row 1 is going to be row 1 minus row 2. And so this means that your new row 1 is going to be 1, 1, let's see, 1 minus 0, 1, and 0 minus 1, negative 1. And then row 2 we haven't messed with, so that'll stay the same. So we got 3, 2, 0, 1. And then we can add negative 3 row 1 to row 2. So row 2 will replace with row 2 minus 3 row 1. And then that turns out that that's going to give us, let's see, 3, 2 is going to, so it's going to give us 0 by design. Negative 3 plus 2 is negative 1. Negative 3 plus 0 is negative 3. 3 plus 1 is 4. And then let's multiply the second row by -1. Everything else will stay the same. So we get 0, 1, 3, -4. And then we're going to take row 1 and subtract from it row 2. So in other words, we're going to replace row 1 with row 1 minus row 2. So row 2 we'll leave alone. Row 1 is going to become 1, 0. And then let's see, 1 minus 3 is going to be -2. -1 minus a -4 will be 3. Okay, so we end up with our inverse being -2, 3, 3, -4. Okay, so that's one way that we could find the inverse. Remember, and I feel like this is worth pointing out just from a time-saving perspective, just from a calculation perspective, if A was the matrix A, B, C, D, what we did in one of the videos before is we calculated that A inverse was 1 over the determinant of A, 1 over AD minus BC, times what you do is you flip, you interchange A and D, so this is D and A. You leave B and C where they are, except you multiply B and C by minuses. Okay, so that's how that's going to work. That's what our inverse is. Let's just check that that's what happened. If A was, so here I'm computing the inverse twice. You don't need to compute it twice. I just want to show you both ways of computing the inverse. There's actually a third way that we'll talk about in general using what's called the classical adjoint, but we'll get into that in chapter 3. So there's multiple ways that we can do this. We can check, let's see. So if A was our matrix, I already forgot what it was, 4, 3, 3, 2. So if A was the matrix 4, 3, 3, 2, then the determinant of A, which is AD minus BC, is going to be 4 times 2 minus 3 times 3, which is -1. So then A inverse is going to be 1 over -1 times the matrix. Let's see, we're going to switch A and D. So the 4 and 2 are going to trade places. And then the off diagonal terms will make negative. So it's -3, -3. And then if we, 1 over -1 is just -1. And if we distribute that through, or rather if we multiply the matrix by that scalar, we're going to end up with -2, 3, 3, -4. Hopefully that's what we got before. And it is. Yeah, we got -2, 3, 3, -4. So that's the inverse. Okay, last step to this problem. Remember that we were solving AX equals B, and that led us to say that X was A inverse times B, where A was this matrix 4, 3, 3, 2, and B was the column matrix 10, 7. So it turns out that our solution to this system is going to be A inverse, which we computed twice now as -2, 3, 3, -4, times 10, 7. And so it works out that this will be -20 plus 21. So that's 1. And then 30 minus 28, which is 2. So it turns out that our solution will be 1, 2. In other words, the system 4x1 plus 3x2 equals 10, and 3x1 plus 2x2 equals 7 has a solution x1 is 1 and x2 is 2. So it turns out that that's our solution for the system.